All right. So I was going to do some of the exercises from this chapter, chapter 2. Let's see, 2.6 through 2.9. Here we go. Let's pull up that page 49. Here we go. It's called bit manipulation. Let's see. Let's do include assert.h, include standard io.h, include standard lib.h. Okay, so we're gonna have some functions here. Set bits takes in x, p, and y, and returns an integer probably. These are all going to be integers. And then we have invert xpn, no y. Then we have right rotation, x and n. And then we had one more, which was bit count. And bit count, if we look back into the chapter here, just took an unsigned x. Okay, maybe these are unsigned, unsigned x. Maybe all these integers are unsigned. Something like that, maybe? I don't know. Let's also ask AI. In C, I thought you could declare multiple arguments, multiple args to a func using just one type if they all shared the same type. Oops. Invalid, but it's not valid in C. You absolutely can declare multiple function parameters the same type in C, but you must repeat the type of each parameter. Okay. Alright, so it's going to be something like that for the prototypes. I guess we'll start at the beginning. So write a function set bits. I'll bring it down here so it's easier to use. And I'll give it a body. Set bits x, p, and y that returns x with the n bits that begin at position p set to the rightmost n bits of y. Leave the other bits in. It just sometimes I need to parse these things to actually know what they mean. So set bits that returns X with the n bits. So n can just be a unsigned. P, beginning at position P, unsigned, P, huh? Oh, rightmost n bits of Y. Okay. I think I understand what they're trying to communicate here. Okay. Just return 0 here. Okay, we'll do let's just do a quick printf of %d size of unsigned. Put a new line here and a semicolon. That's good enough. Make build 4. So we got 4 bytes here. I'm gonna say let's make it a little bit smaller. Instead of 4 bytes, just 32 bits. Let's do maybe unsigned short. Which is 2 bytes. Maybe we can do unsigned char. That'll just be 1 byte. So X and Y are of course going to be the same type. We'll just do a pound defined up here, or we can do a type def, right? Type def. The type will be unsigned char number type name. Like that. Then here you can say num, shorten the prototype here a little bit. And we'll do size of num. There we go. Okay. So let's like visualize some examples here. So I'm just going to bring up the browser to Excalidraw, and we'll do a little visualization. So I'm just going to type out some stuff here. So I'm going to have, oops. Let's do 0, 1, 0, 1, 0, 1, 0, 1. I need to get an extra space in here. There we go. So this will be our what value? We'll say this will be our X value. X. I prefer that not to pop up. Like that. Okay. I think I need another space here too, right? There we turns X with the n bits that begin at position P. So position P would be 0, 1, 2, 3, 4, 5, like that. We'll say P is equal to 5. N is equal to 2. And then we'll have Y as a separate value here. Y, we'll just do the inverse here. 1, 2, 3. 2, 3. There you go. So 0, 1, 2, 3, 4, 5. N is 2. We'll say 3. N is 3. Or 4. Why don't we do 4? One, two, three, 4. Like that. Oops. There we go. And the resulting value X with the n bits that begin at the position P set to the rightmost n bits of Y, leaving the other bits unchanged. Oh, so I shouldn't have inverted this. Okay. If X and Y are the same value, then we're going to take Y and we're going to stack it over this thing and copy over the bits. And so the result will be let's see, 4 here. So 0, 1, 2, 3, 4, 5 should be here, and then 1, 2, 3, 4. So these would be the values, what? On the rightmost would be like, I should have inverted it. So 0 and 1 are going to stay the same, but this is going to be 1, 0, 1, 0. Like that. I think that's what they mean. It has a similar pattern to it as get bits. So get bits, so they're using unsigned, an int, and an int for their types. Maybe I'll use those types. Unsigned, P and N. Let's go ahead and fix those types. So I'll delete this. Unsigned. Just search for num. Int. Oops. P and N or int. Let's pull down their implementation of get bits and work through it, because I didn't fully understand that from the reading. Get bits, unsigned, int P, int N, and no Y. So this one would, I'm going to take this as an example as well. There is no Y. And I think this would be the result, where it just reads between them. These would be zeros. And that'll be a 0. So I think that's what they're getting at with this. But let's test it. So I'm going to just have AI say, hey, give me a function in C that prints out the binary representation of an unsigned. Thank you. What the hell is that? Print binary. We already know it's unsigned from the type. You don't have to do that. Just says, hey, get the size. I don't have to say int. Get the size of x, multiply by 8 for each bit. So that's how many bits. Then for every bit, so we say bits minus 1. I hate this. I get better at reading this stuff. So, can I zoom in on that? No. There's some condition here, and if that condition returns true, we print a 1, otherwise put a 0. Or I'll just do a put char here. Oops. Okay, so while I is greater than or equal to 0, So we're going down, counting down basically. Bits is the length, so we might subtract 1. Okay, so we're saying bits is the length basically, and we're counting down from 1 off the length all the way to 0, inclusive on 0. And then for each of those, we take 1 and we bit shift it out to that amount. And then we AND it with X, which reads out that character. And you say if that is a truthful value, if there's a 1 there, then I'll put a 1. Okay. This totally makes sense to me. It just took me a while to kind of deconstruct what they're doing, because they're iterating in reverse. And they use the bits instead of length, which I would be more used to if I was iterating over a collection. Okay, so that all makes sense. So now let's look at their implementation here again of get bits, which will give return X bits shifted over by P plus 1 minus N, and the negation of 0 bit shift over to N. So this is pretty easy to do. So we say step 1, this part, 1, 2, 3, 4. We'll just do 4 bits to make it, or we'll do 8 bits. So that gives you all that. Let's just say like N is equal to 4. And P is equal to 5. So N going over 4 would make this expression here I think I want these to be on the left-hand side just so that the spacing is consistent. So we say bit shift over that way by n bits. So in our case it'd be 1, 2, 3, 4. Those will all be zeros. And then we take the negation of that and that would have the value like this. Okay, so that's the right hand side. The left hand side, if our x is the value 0, 1, 0, 1, 0, 1, 0, 1, okay, then x what is the higher precedence? Bit shift or logical and? Well, that's in the book here. We got a table here at the end. So bit shifting is here. Logical and is way down there. Or sorry, bitwise and is down here. So definitely does the bit shifting first. So let's evaluate this. So P5 plus 1, 6 minus N, 4, 2. So P would be 5, plus 1 would be 6, minus 4 would be 2. So then if this is X, then X bits shifted over, oh, plus there's a parentheses around this, so that's going to force the precedence. Bits shifted over by that, which would be 2, which caused these two to drop off, and then these would be populated by zeros. Okay. So now we can bring the whole thing together, where we have the whole expression, which is the ANDing of these two. Sorry, the ANDing of this and that. So this would be 1, 0, 1, 1, 0, 1. Which, when we look at our input, hey, how's it going? I'm trying to decipher some of this bit shifting code that they have in here. So if we look back at our input, so 101, I guess that's not really like a good signature since it's a basic pattern, but we bit shifted over 2. So we lost 2 bits there. Okay, so this is basically calculating how many bits to drop. I'm going to add a little comment here. It says, how many bits to drop off the right-hand side. So P would be our position, plus 1 minus N would give us 2. So P being 5, 0, 1, 2, 3, 4, 5. So that's not right. 1, 2, 3, 4, 5. They're treating P as a value that can't be 0. That doesn't make sense to me. Huh. Let's reread the text. As an illustration of some of the bit operators, consider the function getBits xpn that returns the right adjusted n bit field of x that begins at position p. Well, what is position p? Like if p is equal to 0, oh, I see. P can't be 0. If P is 0, then you can't get any bits. You have to have P at least equal to 1. Okay, that kind of makes sense. We assume that bit position 0 is at the right end and that N and P are sensible positive values. Yeah, so we're not going to pass it weird shit. For example, get bits x43. I'm just going to run this as a test up here. So get bits of 4 and 3 of x. What is x? x43 returns the 3 bits in bit position 4, 3, and 2, right adjusted. And if I wanted 1, I would say 4, 4. say I just wanted 1, I would do 1, 1. Okay. So P is generally going to be greater than N. Greater than or equal to N. What's a weird bit pattern here that I could pass in here? Python, binary, 1 0 0 1 0 1 1. Yeah. So 75. And if we do an assert of get bits of that is equal to, basically said, okay, position 4, 0, 1, 2, 3, 4 is going to be 1, 0, 1, which is 5. So in future, I think Google as search engine might end. I don't know about that. They have Gemini now. We'll see. Google is a monolith, so I doubt that they're gonna just like go away. All right, so I'm gonna do one more test here with my values that I had in my example. So 85. Let's do 85 here. Position 4, I'm doing position 5, and length is 4. So that would be 0, 1, 2, 3, 4, 5. I think it'd be 1, 0, 1, 0, yeah. 0 B 1, 0, 1, 0 is 10. So that'd be value 10. Okay, let's go ahead and make that and run it. Okay, we failed. I wish C's assertions would actually give you the reason why it failed. Let's see what the value is. Printf %d, new line. Two. So it's 2. How is that 2? It goes to 4, 0, 1, 2, 3, 4 gives you 3. Huh? There's no way that that could be 2. I mean, obviously their code generates the 2, but three bits in bit position 4, 3, and 2. 4, 3, and 2 would be 1. This code doesn't work, brother. Like, what the hell? Okay, the only way I can guess is that they're saying this is code position 4, 3, and 2, 1, and 0. Okay, that would make sense. So 0, 1, 2, 3, 4, 4, 3, and 2 would be 0, 1, 0, which would be there 2. Okay, so they are counting that first bit as the 0th bit. So let's delete this. We'll call this a 2. And if we do 85 again, bin of 85, we get 5th and 4 bits. So 0, 1, 2, 3, 4, 5. and then we get 1, 2, 3, 4. It'd be 0, 1, 0, 1, which would be 5. Okay. Okay, I mean that's not unreasonable. It's just the way that the language that they use, it didn't really line up with what I was assuming here. So let's go back, just revisit this again. So we got X is the 0, 1, 0, 1, 0, 1, P, N. So the first thing is still valid, which is bit shit over N. All ones, and then negate that. So we have this 4-bit mask. So basically we're saying, give me the n number of bits set on the right-hand side. That's what this right-hand side does. And then this computes 2, which is how many bits to drop off the right-hand side. How many bits to read. And then in here, this will drop off the bits. So in our case, it would be 2. Because that's the thing I don't understand, is like, why is... Can you explain a little bit of context to the kindergarten? So this whole section of the book is about bitwise operators. And bitwise operators operate on the bits of the operands. So you have if you have something like, I'm just going to write some code here. So if you have something like 12 plus, 12 plus 55. So the plus sign is the operator, and then this is the left-hand operand, and then this is the right-hand operand. So these are the operands, and then the operator. And this is what they call infix notation. You could also have prefix notation, which looks like this. Or you could have postfix notation, which looks like this. So these are all equivalent depending on the notation of the language. So C for this operator uses an infix addition, which looks like that. But this is like an operator that operates on the values of the operands, whereas a binary operator, like say we had 12, 5, like this is a bitwise operator. Sometimes they call them binary, but it's a bitwise operator, which means that it operates on bits. So it'll take the binary representation of 12, which is, if I type in bin of 12 over here, is this value, and then it'll shift it over by 5 bits. So if I do that here, you could see how it added 5 bits. It shifted it over by 5 bits to the right. Now you can do the reverse. You can shift it over to the right a few bits, say 2, and you basically drop off these last 2 bits. Or if I did 3, it would just be a single bit. So these are the bit shift operators. And then there's logical operations that you can apply to individual bits. So say I had some binary values here, like 0B 11111, and I wanted to AND that with 0B 00010. So this one has 5 bits, this one has 6 bits. It doesn't really matter. I'll put 2 bits here as 1. And so what this does is it goes through each bit and says, okay, 0 and 1. If I put those together, what is the result? The result is 0. This is basic Boolean algebra on individual bits. And so the result is that we're going to go through each one of these bits, And only where there's a 1 in both places are we going to return a 1 in the result. And so this is basically going to be 34. And if I take the binary representation of 34, you can see how only the bits that were in the mask were set. Now, if I did something like, say I had a 0 here, and then I took the binary representation of this whole expression, you could see how it went through every single bit, and the only one that had 1s in both was the last bit. And so that's the only one that gets set in the last one. And so sometimes people call this masking, because you're basically taking whatever bits are on the left-hand side and masking it with the right-hand side, or vice versa. And so that's and, or is similar. Basically, any bit that's set in either of them will be set in the result. So this will have all the bits set. To illustrate an example of or not setting a bit, we would have to have zeros in both. So I'm just going to put a 0 here, and you can see how that 0 shows up, because there's a 0 here, a 0 here, but all the other ones have at least a 1 in one of the operands. So that's or. There's exclusive or. So this is yet another operator, and this goes through and says, okay, each one, if they are the same, it gets a 0. Only if they're different does it get a 1. And so in all of these 4 positions here, there's a 1 because they're different between the 2 operands. So that's exclusive OR. There's a lot of neat things that you can do with exclusive OR. Exclusive OR is actually a cryptography algorithm. If you have a cryptographically secure random number generator that you can seed with a private key, like a number that only you know, or a symmetric key between you and your person that you're communicating with, all you need is XOR and that pseudo-random number generator, the random string. In fact, you can even make it simpler. You could do one-time pad encryption, which is like you and I, if we want to share messages and have this is the best encryption you can get on the face of the earth, is if you and I have a one-time pad, which is basically a random number that we have shared with each other. And when I go to encrypt the message, every single bit, I do an XOR on with that random number. And then you go and do an XOR as well. If you get the ciphertext, I do an XOR on my plain text to get a ciphertext. I give that to you, transmit that over the internet. Then you take that ciphertext, do the same XOR with the same one-time pad, and you get the original plain text out. So XOR is a really interesting operation. It's fundamental to a lot of cryptography and computer science stuff. So that's this one here, the bitwise exclusive OR. So the last one is the ones complement, which is basically negation. So if I have a binary string here and I negate it with a little tilde, it basically inverts all of the bits, or at least it should. Unfortunately, Python's a little bit wacky and gives it a negative value over here, which is 2's complement. So I would have to do like, I think like this. Is that how I do it? No. It's basically a result of it having a 2's complement representation. If I did it on a unsigned value, it would negate everything. Anyways, so that's what's going on with what we're learning here. And the exercise, before the exercise, they gave us this get bits thing, where you give it a value, a position in that value, a bit position, and the number of bits that you want to read. And they do all this kind of bit shifty stuff. And so up here, I was trying to like decode exactly step by step what they're doing. I have now another question cooking in my mind. Imagine telling all of this to vibe coders. What will they say? I don't think vibe coders really care about this stuff, to be honest. And I don't blame them. Like a lot of this ChatGPT and AI can effectively do what you want. So I don't really blame them for doing that, but I think it's important to understand how our tools and our computers and everything work, because through understanding we're able to innovate and create something new and novel. Whereas I'm not saying what a lot of these people do is not innovative, but like creating a new UI for an app that probably shouldn't even exist. Like I feel like that's that's what a lot of people use ChatGPT for, is creating products that probably shouldn't even exist. But I don't know. I don't want to be too negative on them, but I'm here to understand computers and the vibe coding stuff. Like I use AI a lot to help me understand computers, but it's a tool for me to assist me in my quest of understanding. It's not a replacement for my brain. And I feel like some people just want to use it as a replacement for thinking. But yeah, I don't want to be too hard on them. All right. So to get back to this get bits thing, so I had this test values that I had. So this is supposed to go to position 5. So this is 0, 1, 2, 3, 4, 5, and copy 1, 2, 3, 4 bytes. So 0, 1, 0, 1 is the value that we expect, and that is indeed what we get out of here. So they want us to implement a set bits, and I was thinking through an Excalidraw here before he joins how the set bits thing would work. Never mind this is garbage. So 5, so 0, 1, 2, 3, 4, 5. So that's position 5. Then we go over 4. So that's how it would work if these were our inputs. So let's go ahead. This is enough for us to generate a test case. So I'm just going to go ahead and do that. Set bits. This value of x, I don't even know what this is. So I'm going to say 0b 0, 1, 0, 1, 0, 1, 0, 1. Oops, I need to get in Python. Let's see, 0b. So that's 85 again. And then our y is going to be the inverse of that, which is 0b 10 10 10 10. So 170 will be our y, which I think is the fourth argument. Yeah, 170. And then our position is 5 and 4, and that should generate this range here set from y, which would be 0b 0 1 1 0 1 0 0 1, which would be 105. 105. So we have a test case here. Bring this down. I need to delete this stuff because that's not valid syntax. All right, and then if I make and run it, it's going to fail because we haven't implemented it yet. So how do we implement this? Well, they gave us an implementation of the get bits, which is like probably a good chunk of it. But I want to take this approach. I want to invent my own approach because I feel like this is very heavy-handed. It's a lot of stuff. But yeah, totally agree. Solving a problem and innovating a new thing is totally different things. Yeah, exactly. Okay. So setting the bits. What we want to do is get the bits so create a mask first for the range of bits being operated on. That's my first step. And then I want to apply that mask using ampersand to get the bits in y that will be set. And now how do we set those bits and only those bits in the destination? So that's an interesting question. So let's just go ahead and type out our example, just same as we did up here. Oops. So we have x, and I'm going to do a y here like this. X, y, 5, and 4. So say we have our mask already. So I'm going to grab these. Oops, I need to rename this to be y. X and y. And say we have our mask already. Mask, which is going to be 0, 1, 2, 3, 4, 5. So this will be 1, 2, 3, 4. And then that'll be a 0, and that'll be a 0. So 1, 2, 3, 4. Oh, but we're actually reading it from the rightmost side. I forgot. Let's reread the exercise because I misunderstood this. Write a function set bits that returns x with the n bits that begin at position p set to the rightmost n bits of y, leaving the other bits unchanged. So that means our mask should be like this. So similar to how they generated this mask here. So I'm just going to yoink their expression here because it generates the mask we want. And we'll say this is a unsigned. Okay. So how do we read those bits out and write them into the right location is the question. We could do a rotation. And rotation is actually down here. I really like that this whole thing is like a single expression. And I'm going to break mine out into multiple lines, but I want it to be composable in a way that results in a single expression. Trying to think. We could do a rotation of x, then set the bits, and then invert the rotation. But I don't know how to do a rotation as a single expression. That's the problem. Let's ask AI if there's a way of doing rotation in C in a single expression. Is there a way in C to do a rotation of bits with a single expression? Okay. That's interesting. I think that's what we do, is we do a rotation. So as a prerequisite, let's go ahead. I don't want to use the ChatGPT. I already looked at it, but I want to think through this problem myself. So this is going to be a right rot of x by n. X is going to be unsigned, and n is going to be integer, and it's going to return a unsigned. So we can do a test case for this as well. Let's comment out that because I was failing for another reason. Return 0 here just to get it compiling, and then down here we're going to say assert So if we had 0b, let's do a right rot on 3, and we're going to do it by 2. And that's going to give us a 32-bit value. It's a 32-bit? Yeah, it's 32-bit value. So I'm going to say 32 times 0, the string 0. Okay, so that's 32 bits there. So we can say 0b that, and then the 2 bits will show up over here. So this will be our value that we're asserting against. Okay. And then our left rot will do the inverse. So we should be able to take this value with the bits at the end. And if we left rot at 2, it should give us back 3. So the inverse. And I need to do a left rot definition there. Cool. All right. So right rot. Well, if you take x and you bit shift by n, that'll drop off those 2 values. And then we want to OR them with x left shifted by size of x minus n. Let me get parentheses around this so that the precedence is correct. So basically, most of the work is being done by this expression, x bit shifted by n, but now we have those 2 bits that we lost off the edge. So we can then OR that with the same expression, the same value, but bit shifted all the way over to the size of n, size of x minus n. Or is it n minus, so this will be 2. Yeah, so that'll give us 2 bits. That'll be at the end, and we OR it together. I think that'll work. As lower precedence than minus. Okay, so I need to also do something like this. All right, so let's try getting that to go here. Let's jump over to K&R C. Chapter 2, and we're going to make in here, and my left rot's going to fail, so I'm going to comment that out for now. Let's remake. Okay, we still failed. All right, let's see what our result of right rot is. And I have this function up here that prints the binary, so I'm just going to use that for debugging here. So print binary of, oops, this right rot. Make. Okay, so this is what it resulted in. So if we just do another terminal here for Python, 0b, or just say bin of 3. It's 1 1. It looks like it got left shifted, left rotated. That doesn't seem right at all. If we just did that, what is this thing doing? Why does X... It's rotating to the right. Why is it going to the left? What the hell is this? Okay, we'll try it the other way. That also has that. Is this thing compiling? Yeah, it's compiling. Oh, there we go. Okay, so now it's working. Maybe it was not compiling or something? I don't know. Okay, well now it's doing the left shift again. Let's print out the binary of our value and make sure that's correct, which is this. Make. So this should have 2 bits on the left-hand side. Yep. Okay. Am I... Yeah, so that's correct. Size of X. What is size of X? I would have thought that that would be... Maybe we should say size of unsigned. No. The size of X is correct. If I println or printf out %d new line. So this is going to be size of that minus n. N is 2. Oh, we have to multiply it by 8. Size of gives you the byte length, not the bit length. All right, so that needs to be times 8. And because multiplication has higher precedence, I can do that. All right, that should fix it. Hey, look at that. And we pass our test. All right, so then let's do our left rotation. Let's get our failing test here. So it's doing left is doing a right rotation, which would definitely fail. Just want to make sure it's going to fail. Yep. So our left rotation is going to go left n. So that'll drop off 2 bits at the left side. So what we need to do is we also need to shift this thing over to the right now. Basically the inverse of what we did before. And then it's going to be, we're going to bit shift over plus n. Like that. Make. Doesn't seem to like that. So let's go ahead and get our debug statement going here. Make. Okay, so it did a right shift on it. So I'm guessing I didn't write the file? What the hell? How did that? It's doing some weird stuff here again. So let's comment this whole thing out. Do another make. So make. Okay, so we have 0 bits, which is expected. That's exactly what we expect. Okay. Then we take X and we right shift it. This still needs to be minus n because we're right shifting. Yeah. Okay, I think that'll fix it. Okay, that fixed it. Cool. All right, so we have our left rotation and our right rotation. So now up here, what I'm going to do is I'm going to take x, and I'm going to right rotate it n number of times. So I'm going to say unsigned rotated is equal to x, or we'll say a right rot of x, and we want to do n number of bits. So now if I go here, the right rotation would look like this. Right, or rotated. And because it's even, n is a 4, it'll basically be these 4 are rotated with the other, which is the same thing. So now we take our y values and we apply them to the rotated, and then we undo the, I'll have to forward declare these guys. I'll just pull them up now that they're done. Pull them up above here. So we have these 3 values. We have y, mask, and rotated. And we want to combine them together so that we get the bits from y. So where there's a 1 here, we want to get bits from y. And where there's a 0 here, we want to get bits from rotated. I'm trying to think how to do this. So we can get bits from rotated, or sorry, from y, by saying and with y. So if we and y and mask, we'll get 0, 0, 0, 0, 1, 0, 1, 0. So that will get us part of the way there. And then I think we need to do a and on the negation of the mask, which will get us the bits over here, and then we OR them together. That's what we need to do. Sorry, I missed your question here. Out of context question break. Why Chinese are open sourcing the AI models like Rain, Alibaba open sourcing their models? Generally, in the history of all computers that I've been dealing with, the loser open sources. It's a competitive advantage when you're behind to open source. And we've seen that in AI with Meta and with China. And even initially with OpenAI, is that if you're behind, you go open. And it's a way for you to catch up, basically. None of the market leaders are open. Once you're the leader, you close everything down. That's generally been the trend of technology that I've observed over my lifetime here. It's been more than 10 minutes and Marchi is installing and installing. Oh, wow. Usually it shouldn't take that long. Marchi usually takes like a couple minutes. They pride themselves on saying that it only takes a couple minutes. So I'm surprised it took 10 minutes. The only time it's taken me a long time to install a Marchi was on my Alpine, or not my Alpine, my Asahi MacBook, because it's not really like a very well supported installation. Oh, you're on VMware? Yeah, I can see why that might slow it down. Okay, cool. I think we got a solution here. It's not going to be an elegant one, but we're going to take Y and we're going to AND it with mask. And what that's going to do, that's going to give us a value that's a partial. So we'll say partial A, and then we're going to do another partial B, which is the X ANDed with the negation of the mask. And then we OR these two things together. And in fact, I can just do that as a single expression here. I don't need to have these intermediate names for these things. So that's the expression. And OR has lower precedence. If we look at our precedence table here, where is it here? So the bitwise operators are here, and AND has a higher precedence than OR, just like the Boolean, the logical operators. So that will give us the result that we want, but then we need to rotate this back. So I'm going to say return this value, and we're going to rot left it. Rot left. And we're going to give it n. Sorry, left rot, not rot left. Left rot. And I think that'll give us the right answer. Make. And let me get my test case here. Set bits. Make. Ah, damn it. Something went wrong. Okay, so let's get our print binary debug thing here going. So I'll grab set bits. Okay, let's see what the actual value here is. Make and run. Okay, so what was I expecting? Not this. What we need to do is compute this along the way, like print stuff out along the way here. So I'm going to go back to pulling these out as sub-expressions just to be able to print them out. Unsigned what we call partial A is equal to that partial B. Let me do this. In fact, I'll just call these A and B since they're temporary anyways. And then we'll call this pre-rotated. Pre-rotated is going to be the A or B. And then the final value will be left rot or pre-rotated. So we can track every step of the way here. I could also attach a debugger and step through things. Somehow it's stuck on the login screen even though the password is correct. It's not going to the main screen. In your VMware settings, did you give it like enough CPU cores and stuff? Like sometimes if you don't have enough memory and CPU for the VM, it'll just like not work. All right, so I'm gonna print binary out the mask, and also do like a print F here and say, hey, mask is equal to that, and then we'll do rotated. Oops. And then we'll do A and B. So A. I'll put these right next to the assignment. B pre-rotated. Pre-rotated. Okay. Let's try that. Make and then run it. And then I should probably pad these things so that they're all aligned well. So what is this? I'll just do correct. Oops. Place a space A B. A Is that right? Looks right. And then mask here. All right. Let's try that. Okay. It did it twice. I didn't expect that. Oh, because I did actually run it twice before I did the assertion. Okay, that makes sense. All right. Yeah, I should probably do the same thing with X and Y, right? We'll say 1, 2, 3, X and Y. All right, make. All right, good. So we got our X here, we got our Y here. We got our mask and bits. We then rotate our X over. That worked. Then A is going to be the bits from Y. Yep. And then B is going to be the bits from, and then pre-rotated is the combination. And then we rotate over 4 again. The problem is that at some point we lost these bits over here. You see that? When we went to A and B, we lost those bits. So our mask didn't mask correctly. So we applied the mask to A. That seems right. And B gets applied to X when it needs to get applied to rotated. Who's taking rotated? Rotated. Oh, that means that we don't have to apply the rotation again. Okay. No, we do have to apply it. Okay. All right. So we have these bits. And then I wonder if this rotation stuff is like even a good idea. I want to apply the rotated bits. I don't want this B value. Yeah, this B stuff is no good. Let's just do away with it. And we apply the Y, the mask to the Y. Well, I think B needs to be applied to the rotated, right? B need is applied to rotated. There we go. And then we OR them together, and then we rotate back. Okay, let's try that. Make well, it looks like we got something. Let's see. It's not the right value, obviously. It's inverted. I'm wondering if this rotation stuff is even like a good idea. So you rotate it over, reset the values. We should be only rotating over 2 though, right? So 5 would be 0, 1, 2, 3, 4, 5. And then we'd have 0, 1, 1, 0, 1, 0, 0, 1. That's what we want. Instead we got 0, 1, what is this? 1, 0, 1, 0, 0, 1, 0, 1. The rotations are weird. Oh, because this needs to be right rot N. We actually need to right rot P minus N. Yeah. And then we need to undo that with the left rot P minus N. Make. Oops. So that got us the right rotation. So A value is wrong. A value and B value looks a little wrong too. But A value needs to be, no, B value actually looks correct here. A value needs to be the bits from Y. That is correct. Wait a minute. The mask is 4 bits because our N is set to 4. We're going to want to copy 4 bits. So set bits at position 5. 0, 1, 2, 3, 4, 5. So that means that we should have a 0, 1. Oh, it's because it's the rightmost. I think my algorithm's correct. I think, so let's just get out the values here. So 0, 1, 0, 1, 0, 1, 0, 1 is the X value. And then 1, 0, 1, 0, 1, 0, 0, like this, is the Y value. Now if we set bits in here, we go 0, 1, 2, 3, 4, 5. Let's see, 0, 1, 2, 3, 4, 5. That'll put us here. And then we have to get 1, 0, 1, 0 in there. So it should be 0, 1, 1, 0, 1, 0. But this one, the rotated is isn't rotated enough. It's, so the original bits start at 0 here. So we should be ending at 1. The rotated is off by 1. I think it's P plus 1. Yeah, P plus 1 minus N. Similar to how they did it up here. In their implementation, they did P plus 1 minus N. Exactly. So I just rediscovered the offset that they had in theirs. Okay. Make, build. Hooray, it works. All right, so let's get all of this stuff out of here. The printing. And I'm going to try to just combine this. I know it's kind of like, why make it terse, but why not? So anywhere that we have rotated, I could just replace with this. Like that. And then anywhere that I have mask, nah, it's too ugly. The expression would be really gnarly. I'd rather just make it clean like this. I mean, use nothing but binary bitwise operators because right rot and left rot are both implemented with bitwise operators. The only thing that's different is the function call here. I'll delete this comment here though. Okay. Not quite as elegant as their solution, but not bad. And then I'll delete out this. And we'll just say make and rerun it. And it should be good. Okay, cool. So let's go back to the exercises. So the first one is write a function set bits that returns x with the n bits that began at position p set to the rightmost n bits of, this is the thing that got me, tricked me up, was the rightmost n bits of y, leaving the other bits unchanged. So that one is done. Write a function invert that returns x with the n bits beginning at position p inverted, i.e. change 1 to 0 and vice versa, leaving the others unchanged. And then finally write a function right rot that returns the value of the integer x rotated to the right by n positions. So I want to see what the ChatGPT rotation implementation was, because I used size of, and I think they just made the assumption that it was 32 bits. Yeah. I mean, I did size of x, which gives you 32 times, size of gives you 4 times 8, which gives you 32, minus n. And then if it's a left, that's a left rot. Yeah, they just hard code the assumption of bit lengths in theirs instead of using size. Okay, so they have a size of version here, which is pretty much exactly what I did. So x, and this is a left rot here, rotate left, and then x, rotate right, size of x times 8 minus n. Yep, exactly. So I'm glad, I looked at this stuff. Oh no, sorry, I looked at this stuff here, and then I backed out. So I didn't cheat. I actually did implement it myself. Everyone facing these problems, especially on VMs and some even on laptop. Oh really? I didn't know that. I haven't had any issues. Actually, I take it back. I have had one issue. I had to patch out some garbage in their Chrome shortcut that they didn't template out correctly. There's like an open issue for that. It doesn't seem like they're maintaining it very much. I even submitted a PR for something and they haven't even commented on it. So, all right. So the next thing is right rot, and then bit count. Or sorry, we already did right rot. Next one is invert and then bit counts. So let's do that one. So invert is just inverting all the bits that starting at PN. So that would be easy. We'll just do 0B 111 1 1111, and then that's 255 obviously. So here we say assert that invert of 255 will be starting at P. So P will be 5 again. So 0, 1, 2, 3, 4, 5, going for 4. So that would be 1, 1, 0, 0, 0, 0, 1, 1. And if I do that as binary, 195. So we'll do the same thing, 5, 4, since I'm used to those offsets by now. That would be equal to 195. So let's get our invert going here. This one I think I can handle without a lot of statements, because they have the expression right here. So this is to read it. So how do you negate using a mask? Exclusive OR. So instead of anding, we're going to exclusive OR it. And we might have to negate this thing, or undo one of the negations. Oops. What's going on here? Oh, I forgot to put a semicolon. All right, make. Okay, so we got our core dumped. So I'm just gonna throw this over and say, okay, we're just not gonna negate the mask and see if that actually solves it. Nope, it didn't. Okay. Well, let's step through this. So print binary. Oh, we have to shift it over again. Let's just implement our own version of it. So we're going to do something very similar to set bits, where we develop a mask, we write rod it, except for there's no Y. So we're not going to be anding with Y, we're going to be anding with I think what we want to say is this, and this will be pre-rotated. Oops. Like that. Okay, let's try that. Make. Okay, it didn't work. And let's take off the inversion of the mask. Make. There, it worked. That was easy. Okay, let's do an invert on something else, like maybe 6 and 3. Sorry. 6 and 3. So that would be 0B1 0 0 0 1 1 1 1, which would be 143. So just add another test case here, so make sure, keep us honest. Yep, everything works. So inversion was easy, and the last one was bit count. So that was a different section here. So there was a bit count that was already implemented here, so I'll just copy that implementation. So we have unsigned x for, sorry, int b for b is equal to 0, x is not equal to 0, x bit shift equal 1, if x and octal 1, I don't even know why I need to do an octal 1 there, then b plus plus, and then at the end we return b. So that's counting how many bits. And I messed up a semicolon here. So this condition is saying, so long as there are bits in X, we're going to shift them off, and if the new value, we're going to shift one off, and if the new value, no, this is after. Sorry, this is after. So long as we have bits set in X, then if the rightmost bit is set, then we're going to increment it and then shift it off. That's what this says. So you're not in their Discord channel. There are a ton of people there. Yeah, I'm in their Discord. I hopped on their Discord when I submitted a PR, but then no one wanted to merge my PR, so I haven't really been active on their Discord. So the exercise for this was in a 2's complement number system. X and equals x minus 1 deletes the rightmost 1 bit in X. Explain why. Use this observation to write a faster version of bit count. All right, so in 2's complement number system, x minus 1 anding it with that deletes the rightmost bit. Well, let's just do some bit printing here. So print binary. We're on a 2's complement system here. So we'll say int x is equal to like 12 or something. I don't know. We're going to print out 12. And then we're going to print out 12 minus 1. And then we're going to print out 12 and 12 minus 1. And we'll just see what these values are. Make. So this is 12. The 12 minus 1 just on positive numbers will remove a bit. And then if we add it together, I removed a lot of bits. 12 minus 1 and equals. Yeah, 12 minus 1. That did not delete the rightmost. No, that's. Well, we'll do it differently here. We'll just print binary x. And then we'll do it literally what they said here, which is x and equals x minus 1. And then print the binary. Oh, it drops the rightmost bit. I see what they're saying. Not the least significant bit. Like literally the bit on the right-hand side. Like if we had something else. What's another binary that we could have? Let's do a different bit pattern here. So we'll do 111 0000 like that. 112 112. Make. So yeah, it turns the rightmost 1 to a 0. So to figure that out, let's do x minus 1 as a partial value. Make. So x minus 1 is obviously gonna like flip the rightmost bit, because that's what subtraction means in binary, is that you're gonna flip that bit and then turn all the other ones to the right from 0 to 1, and then you AND these two together, and naturally everything here and here is going to return 0. Okay, that makes total sense. So the nature of subtraction in a normal binary counter is such that if you subtract 1, the rightmost bit is going to flip to a 0, and then all the zeros to its right are going to flip to 1s. And then if you AND those together, by definition, a 1 turned to a 0 and a 0's turn to 1s, so all of those can't be ANDed together to get it. When they're ANDed together, they get 0's. So that means that anything left of here is going to be preserved, anything right of here is going to be 0's. So that effectively drops the rightmost bit. So I understand that on regular binary, but now let's do like a negative number. So let's do like negative 12, 112. Sorry, make. So that's very similar. So subtraction will, instead of doing flipping the rightmost bit to a 0, it basically flips the rightmost bit to a 0. Yeah, so it does pretty much the exact same thing. Yeah. So subtraction is the same operation in 2's complement, whether you're positive or negative. So we're going to get the rightmost bit flipped when we negate it, and all the zeros turn to ones. Yep. Okay, so knowing this fact, we want to implement a bit count. So I'm just gonna get a test case for the bit count. Bit count of 12. Sorry, bit count of 12 is going to equal 3, and bit count of, what was this, 112? Sorry, 12 was up here, 2. So binary of 12 is 2 bits. 112 would be 3. And let's do the negative as well. Negative 112. There's a lot more bits set. So negative 112 would have all of these set here. So we'll just do a len of this string, if I can type right. And then I'm just going to delete all the zeros. Give me back 26. 26. So first I'm going to make sure that bit count actually works the way expected with my test cases. And that works. So now we get to re-implement bit counts using bit shifting. So return so here we're still going to have to count. But instead of bit shifting off the end, we're going to do a ampersand equals of x minus 1. Hey, still passes. So it's slightly faster. You're still iterating through every bit to count them, but you're just dropping them. I don't know. It's probably not too much faster. But yeah, there we go. All the exercises are done. Those are fun. I don't know if you could follow all of those, but I had fun. I haven't yet logged into the main screen. Gonna have to fix the issue now. Why it's even happening in the first place. So what's the YouTube link? What link are you referring to? Oh, it's not in the bio? I thought I added it to my bio. So this is the YouTube link. And there's a playlist with all the live streams, or you can just go to live. Yeah, this is where all the streams are. If you just go into streams. Update the bio. I guess you're right. I should update the bio. I thought I already did that. Let's see. Twitch.tv Cypher0Dev. Yeah, there's like a YouTube link right under the About Cypher0Dev. There's like a link to YouTube there. I don't know if you can see that. Is there like another bio that I should add this to? I'm really bad at this stuff, man. Oh, do you mean the Discord stuff? I'm confused what you're talking about. Let me hop on Discord here. Maybe you're talking about that. I don't think I have any of my stuff linked on Discord. I could add my pronouns. I guess I can add it here. Oh, okay, thank you. Oh, you said my YouTube link is pointing to Twitch because I fucked it up. I got you. Let me fix it. I don't even know how to fix this shit. Yeah, it just goes to Twitch. At least my GitHub works. How do I freaking edit this shit? Man, I swear I hate computers sometimes. Alright, let me go here. Channel, maybe? Settings? No. It would be under channel. Why can't I just edit? Maybe it's because my window's too small. Edit here? No. Because that's the actual broadcast. Man, it doesn't let me edit this stuff. Maybe because I'm live streaming right now, it's like... Let's try creator dashboard. See if it's under here somewhere. Settings, stream. No. Channel. Here we go. Yeah, you're right. I just did the wrong one. My bad, my bad. Thank you for catching that. I appreciate it. Alright. Let's fix that. All right, so that should be fixed there. And then I'm also going to add my GitHub to my Discord. Because I was had that thing not set correctly. All right, add it here. Bam. All right, what's your other question? How to patch the solution to the image and how to test it. You mean the Omarchy image? Well, I would start with like looking at their repo and try to build the image from their repo. Usually they'll have build steps. I actually haven't looked at how they do their builds. We can do that together here. So let's go to Omarchy, GitHub. Whatever. We'll just click on GitHub. So the ISO images have to get built somehow. If you look under actions on master, maybe. This is just some TypeScript analysis thing. This is not it. Let's see if there's a different repo for this. Sometimes they put it in a different repo. Let's look in here for build. Nope. ISO. Let's ask AI. How does Omarchy build their ISO images? Where is that code located? Okay, so they got some weird ass repo here that was not the source repo. Here, let me give you this link here. Well, yeah, I use OBS. github.com/omacom-io/Omarchy ISO. So that's how they build their ISO image. So the Omarchy ISO streamlines the installation of Omarchy. It includes the Omarchy configurator as a front end to Arch install and automatically launches the Omarchy installer after base Arch has been set up. Creating the ISO. So you run this thing. So you make your changes to this repo. Then you run bin Omarchy ISO make, and the output goes into release. You can build from your local Omarchy path. So if you have the repo set up, you could set this environment variable Omarchy path to point to that repo, and that would be this repo here. For testing, use local source or from a checkout of dev branch instead of master, use --dev. So you got the Omarchy installer repo, Omarchy ref. So you can actually point to a different repo on GitHub, I guess. That's interesting. And a different location instead of master. What changes are you making? I've only had to make changes to the Omarchy repo here. And that's stored if you go under local share Omarchy. That's where that is. So you can see the upstream here. Hyperland is crashing on VMware. Do you have to use VMware? I mean, VMware kind of sucks. What is your host operating system? Is it Windows? Windows 10. Okay. Have you heard of this project called Vagrant? So Vagrant is like a CLI that allows you to boot virtual machines on your local machine, and it has different backends, and it provides the disk images for you. This might not be ideal for your situation, but what's nice is that they have different backends documented. So, they probably don't even support Windows. Oh no, they have binary downloads for Windows. Let's look at the backends. Providers? Yeah, here it is. VirtualBox is the one that I have the most familiarity with. I've used VMware in the past for a few things, but that was like a long time ago, like over a decade ago. I actually used to work at VMware, incidentally. VirtualBox now crashed so much. I mean, you shouldn't have your hypervisor crash. That shouldn't happen that often. Does it crash like you get a explicit error report, or is it a crash like it just goes slow? What is this Hyper-V thing? Vagrant comes with support of the box for Hyper-V, a native hypervisor written by Microsoft. Why aren't you using this Hyper-V thing if it's built into Windows? Sounds like kind of like KVM for Linux. Might be the image problem. Yeah. I don't know. I've never had that issue. Yeah, I'm sorry you're having problems there. That sucks. I tried Kali Linux and I got problems. Maybe Microsoft just doesn't want you installing Linux on a virtual machine. So they're just like deliberately crashing it. Yeah, I mean, my best guess, and this is just a total guess, is that you probably don't have enough system resources to be running the guest operating system and the host operating system. So like what I would recommend is like shutting down everything on the host operating system that's not absolutely necessary, and then going into your activity monitor thing. I forget what they call it on task manager, I think it's called on Windows, and like just finding anything that's consuming memory or CPU and just killing everything. And then once your host operating system is like free and has a lot of spare resources, then go into the configuration of your virtual machine and allocate specific cores and a huge chunk of memory to the virtual machine, and then make sure nothing runs on the host still, like while you're running the VM, and then you'll get pretty decent performance, assuming you have enough cores and enough memory. Windows, from what I understand, I haven't used Windows in like well over a decade, but it seems like it's like kind of like a piece of crap nowadays. So it might be that it just like the host operating system's consuming all your resources. Okay. Yeah, it seems like you have a lot of CPUs. Yeah, I mean, that's a lot of CPUs. And your memory, you're using 21 gigs out of 80. I mean, that's still plenty of gigs. I mean, you shouldn't be having issues booting a Linux virtual machine if you have this much resources. $30 each on Alibaba. Wait a minute. Do you have? I thought these were CPU cores. Yeah, you have Intel Xeon. It's a 2 gigahertz. Yikes. I mean, 2 gigahertz. I mean, it's nothing to scoff at for sure, but it's just like really old at this point. I mean, I was running like a 3 gigahertz processor when I was like a teenager. I mean, there's a lot of cores on the CPU, though. It's kind of crazy how many cores there are. 32 cores. And it's a dual socket CPU. It's a 2 gigahertz dual socket 32 core Xeon. And you have 64. You have hyperthreading too, so you have 64 logical processors. That's kind of silly. I could get upgraded to Xeon 4 series, but that CPUs are expensive, yeah. I used to run a Xeon at a data center for a server that I was using for about a year to mine Litecoin. back when you could CPU mine Litecoin. All right, so where was I? Boom, boom, boom. All right, I think, yeah, this is a good place to stop here. I'm pretty happy with all the bit manipulation stuff. We fully understood the get bits implementation. I was able to very easily implement a right rot and a left rot. Those are not hard to implement de novo. This set bits, the inverts, and the bit counts, I wasn't super happy with. But they're all using nothing but like arithmetic and bitwise operators. So in that aspect, I'm happy with them. But I think there's plenty of room for these to be optimized still. But yeah, that was a fun little experiment. So let's go ahead and add those. Do I have a get ignore here? I do not. So I'm going to echo build into .get ignore, get at all, get status, and then cat makefile. Okay, it looks good. Make clean. And get status vim up the readme. And we'll go to chapter 2 and mark that as done. So some things that I feel like I can improve upon is the speed at which I did this. It took me a while to understand these bit expressions, the bitwise operator expressions. So I think moving forward, if I'm going to parse out an expression like this, what I should do is just extract out and give them names like I did here. And that'll just help me kind of have a logical understanding of what's going on. And then doing this type of commenting also helped me as well. But yeah, I could have gone a lot faster in implementing some of this stuff. So we'll just do, what is it? Git CI, finish chapter 02. Push that up. That'd be our work for today. So that was, how many pages here? About 54 pages. So if we do about 50 pages a day, let's run a calendar. So that would be 100 roughly. So probably by like the start of next week, I should have this book read and done. It depends how many exercises I do, I think. But this one's going to be a short one. It's not going to be too long. Plus, a lot of this stuff I already know. I feel like I'm getting most of the value out of just like doing the exercises on this one, because there are some interesting exercises that I haven't really explored before, like all the bit manipulation stuff. Those are fun. And there are some things that I learned outside of that just in the reading. And yeah. There is this old syntax for C89 functions that I thought was interesting. The reason why you need void in your argument list is also like really interesting. There's a paragraph in the beginning of this chapter that talked about how a lot of the symbol names for assemblers and linkers and loaders have these constraints on how long they can be. And I was thinking that's probably why C has so many variable names that are short. It's just because these programs have kind of, and this programming style has developed in an environment where your symbol names could only be so long. So I am learning stuff just from reading the text. But yeah, I guess tomorrow we'll get started on chapter 3, and that'll take us ideally to maybe about 100 pages. So that would be chapter 5, pointers and array. Oh, and pointer arithmetic. I want to get really good at pointer arithmetic. I mean, I am kind of decent at it, but yeah, I want to get like really good at it. Let's see. So 100. So we'll definitely get 3 and 4 done tomorrow. We'll probably do control flow, functions, and program structure. And then I might start on pointers and arrays just because like this is like, I mean, I know most of it already, but like there's a lot of weird pointer stuff that I only have familiarity with. So hopefully they get into some of that weird stuff. Yeah. Cool. Let's see. Well, what really was interesting, you solved the problems by completely analyzing and revising your own approach. Yeah. It just took me too long. I wish I was faster. Like some people can just like look at like a binary bitwise operator expression and just immediately understand what it's doing. And I just don't have the reps to be able to do that. So it took me a long time, like even before you hopped on the stream, it took a while for me to actually understand what those things are doing. I did leak code before for interview prep in the past, and I would do it all by hand. Like I had a like a marker board that I would draw all of my write all of my solutions on, and my goal was to be able to one shot them. So like you give me the prompt, I work through developing a solution, and then I literally type in character by character into leak code, and if it doesn't compile, I don't get credit. That was my goal. And it was like over 100 solutions that way. I felt that really helped me prepare for some of these interviews where all you have is a whiteboard during the interview, and you can't, rely on AI or, a language server protocol, module, or your editor and IDE. Like, there's all these tools that we use to like help us program, and they're awesome for going fast. But if you don't have those, can you still program? Like, some people can't. Some people look at a blank page or a whiteboard and they just can't write code, which is crazy to me. Yeah, I mean it's great because they have a huge spectrum of different problems that you can work on. There's actually a book that I might start reading this year, depending on whether I decide to get a job or not, which is Beyond the Coding Interview, or Beyond Cracking the Coding Interview, this one here. So I read the first one, which was Cracking the Coding Interview, and then this is supposed to be like the next step, upgraded for the modern era. That's Python, isn't it? Curious why they use that. An exit for, yeah. This is probably Python's exit. Yeah. So these guys are probably Python guys. I think Python's a great language for doing interviews in, because it's very forgiving syntactically, and there's less syntax, So you don't get trapped up on syntactical stuff. I think dynamic programming, I did a lot of dynamic programming, DP problems when I was doing interview prep, but that's something that I could spend some more time with for sure. I have a whole book on this stuff, CLRS, Introduction to Algorithms. This guy here. We might do some of that this year, just for interview prep. All right, well, I'm gonna hop off. It's getting kind of late here, but yeah, good progress today, and I'll be on tomorrow. I think the entire day I'll have free to work on this. I don't think I have anything else going on. No gym in the morning, no nothing. So yeah, I'll be on in the morning, and yeah, continue to make progress on this. Cool. All right, see you later.